Okay, let's first discuss one thing that I always think of discussing but always keep forgetting. So it is about the local attraction and correction of the local attraction. Remember when we were doing compass surveying, we studied about forebearing and back bearing, and it was like this, right? So we have a point A, we have a point B, and we are getting out our surveying work from point A, then we go to point B, then we go to point C, like that. So we had a line, something like this. The north was here. So from the north, in clockwise direction, the angle made to this AB line, this is our bearing. Remember? Now, when we find out the bearing along our way of work from A to B, if we find a bearing, that bearing was called as forebearing, right? Now, after finding out forebearing at point A, if we go to point B, we will still have the north in the same direction, almost, right? And then again, when we measure the angle or bearing in the clockwise direction, this will be the value. Now, this is still bearing, but since we have measured from B point to A point in the reverse direction of our progress of survey work, this is termed as back bearing. I think you remember this much. And we also saw that if this is a straight line, if you produce this straight line, then what will happen? This angle is going to be 180 degree because this is a straight line, right? And this angle is going to be this angle by the rules of trigonometry. So we knew that the difference between back bearing and forward bearing should be 180 degree. We knew that. So, but if in some cases, if the forward bearing and back bearing is not 180 degree, then at that point we have some instruments, some influences, some magnetic influences that are changing the magnetic bearing values, right? So that is local attraction. Okay, there are some notes about what is the definition of local attraction. We know that already, but what type of influence, what type of instruments may influence, etc., etc., are there in the notes. Please see that. Now here, what we want to discuss: what to do when we have local attraction. So when we have local attraction, the difference between forward bearing and back bearing will not be 180 degree. It will be maybe it is 181 degree, or maybe it is 179 degree, something like this. So here we have an error. Here we have an error of positive 1 degree. Here we have an error of minus 1 degree, right? So we will carry out our work like this, right? We have AB line, we have its forward bearing, we have measured its forward bearing, say for example 10 degree. We have its back bearing, say for example it is 191 degree, right? So what is the error here? The error, we see that it is plus 1 degree, right? Because 191 degree minus 10 degree is how much? 181 degree. So it is not 180 degree, it is slightly greater than 180 degree by 1 degree. So that is our error. So there can be two cases. We are going out, carrying out our survey work from A point to B point, then C point, then D point, then maybe E point, and then we come back to this point, right? So if we have a situation like this where we are coming back to the original point, then we have a closed traverse. Now, when we are doing a closed traverse, we will know the summation of the angles, right? So if it is a triangle, it is 180 degree. If it is a rectangle, no, then it is a, or quadrangle, it is uh, 360 degree. And then like this, we have this formula 180 degree into n minus 2, right? Where n is the number of sides. From there, what we can do, we can find out what should be the angle. And from these bearings, we can find out what are the interior angles. And then we can find out what is the difference. Say, for example, we are finding out for a triangle, right? From the bearing, we saw that we will calculate the interior angles. And we saw that the interior angles is not 180 degree, it is 181 degree. So that means we have made an error of 1 degree in calculating the interior angles. So in case of triangle or in case of quadrangle or any closed traverse, so if it is something like this, so the summation of all the interior angles should be 360 degree. If it is not 360 degree, if it is 361 degree, that means there is an error of 1 degree. We have measured 1 degree extra. So that 1 degree extra has to be subtracted, right? It has to be subtracted. Then only we will get the correct value. So it has to be minus 1 degree, our correction. So we have 4 angles and we will divide the 1 degree in all the 4 angles equally. Okay. That way, these interior angles will be changed. Okay, 1/4 here, 1/4 here, 1/4 here, 1/4 here, and then when we will again add them up, now this is going to be 360 degree. So that is one way of correcting the values when we are carrying out a closed traverse. But when we are carrying out a open traverse, right, we are not closing down, we are not coming back to the original point. From A point, we went to B point, then we went to C point, then we went to D point, and we ended our work like that. So there what we will do, we have AB point, we have BC point, BC line, we have CD line, like that. So here we will have forward bearing, here we will have back bearing. So their difference should be 180 degree. If it is not 180 degree, there will be an error. And the correction will be opposite of error, right? Now, in the numericals, book numerical, there will be always one line, say always one line, say for example, CD line. That in the numericals that we see in the book, there will be always one line given to us where the difference between forward bearing and back bearing is exactly 180 degree. Now, when we see that line, that means this CD is correct, right? There is 180 degree difference. There is no error. That means station C and station D are free from local attraction. Okay. Now, when station C is free from local attraction, that means the measurements made from station C must be correct. Now, take the example of BC line. In BC line, we calculated forward bearing and we also calculated back bearing. When we calculated forward bearing, we calculated from B point. When we calculated back bearing, we calculated from C point. So since C point is now free from local attraction, so what will happen? This is free from local attraction. Okay. So therefore, what will happen? The measurements made from C point should be correct. So the back bearing of BC line, we will consider that back bearing of BC line is correct. Why? Because the back bearing was measured from C point and C point is free from local attraction. So whatever is the difference, say for example, the difference is 182 degree. Okay. So the error is plus 2 degree and the correction is minus 2 degree, right? So the value of 4 bearing will be changed by minus 2 degree. Then the difference between these 2 points will be 180 degree. Okay. Like that, we will carry out our work when it is numerical in the book. Because in the book's numerical, most of the time, we will be given at least one line where there is perfectly 180 degree difference. And from there, we can calculate the other values, considering that, okay, CD line, the difference of back bearing and forward bearing is exactly 180 degree. So these measurements are correct. C point and D point are free from local attraction. And then from there, we will carry out the other values. But what we do in the field, maybe everywhere we have local attraction. So in the field, we will consider the line where the attraction, local attraction is minimum. That line we shall consider, and we shall divide the values between both these stations, and we will consider the line where minimum local attraction is seen. We will divide the error in both these stations suitably, and then we shall consider, okay, that line is error free, and then we will consider proceed in the same way. So this is about correcting local attraction in numericals where involving forward bearing and back bearing. Okay. So after this, okay, after this, we will go to triangulation that we were discussing in the last class. If you didn't understand the, or if you have any confusion in the local attraction and correction of local attraction part, please let me know. We shall discuss again. Now here, now we have a concept of errors. Okay. Now, when we carry out measurements in the field, be it surveying, be it other branches of engineering, okay, be it structural design, there is always some kind of approximation. There is always some kind of probability of failure, probability of being not true is involved. Okay. Say, for example, very simple example, we are measuring a distance between 2 points. Say, for example, if I measure, maybe it is, say, for example, 21 meter. My friend measured, maybe it is 21.5 meter. Some of you measured, maybe it is again 21, again 19.5, like this. Okay. So the thing is that we don't exactly know what is the true value in some of the measurements. So there is always a probability of error. There is always a probability of not being exactly true in all the branches of engineering involved. So we will discuss about that theory of errors here. So first of all, we have a definition of precision and accuracy. So this is a diagram here which tells us about what is precision, what is accuracy. If we start here in this figure, the central red dot, we are assuming that that is the true value. Okay, but the black dots here, those are our measurements. Okay, so in this value, our measurements are haphazard. Okay, say for example, the 100 was a true measurement. Our readings are 50, 60, 80, 90, 110, like this. So our measurements are different from each other, and it is also not close to the actual value. So this is a case of low accuracy and low precision, right? Then in the second one, our values are kind of 60, 61, 62, 59, like this. The actual value was 100. So we are nowhere close to the actual value. but our measurements are close to each other. Fine. So there is high precision. That means our measurements are almost same. There is precision, but it is not actually the correct value. So low accuracy. Then here in this third diagram, we see that the values are like, say, for example, the red dot, the central red dot is the true value, right? So the values are like 98, 105, 90, 110, like this. They are closer to the actual value, but they are not exactly, closer to each other. They are again haphazard, but they are somewhat closer to the original value. So here we have a high accuracy and low precision. So precision will be the uniformity among our measurement, and accuracy will be when our values are closer to the true value or actual value. And here in the fourth diagram, all the values are close to each other and also very close to the original value. Okay, we are measuring 99.5, 99.8, 100, 100.1, like this. So here we have high accuracy and high precision. So this is the concept of high accuracy and high precision. Now, errors. In surveying, we can make, there are a lot of errors we can make, okay? So it is basically classified into three categories: gross errors or mistakes or blunders. So this is for carelessness. We are making a careless effort. We are making some procedural mistake. Okay? We are not following the correct procedure of measurement. Okay, that type of, we are saying that uh, the value is 20 meter. Our friend heard 30 meter and recorded 30 meter. That's that type of gross error or mistake, okay? Because we are not careful in the field. Very simple. Systematic error will be the next category when we have instrumental error, right? So we had a tape of 30 meter, but it is not actually 30 meter. It is written as 30 meter, but it is 29 meters. So there is a systematic error. Every time we measure 30 meter with the tape, actually we are measuring 29 meter only. So that type of error, or errors that are occurring due to temperature, etc., just like we discussed in the last class, the numericals, those are there in systematic error. And then there are some errors which are accidental errors or random errors. Okay. So these are beyond the control of the observer. Okay, so these are sometimes positive, sometimes negative. Okay, they are going to be there all the time to some extent. Okay, so these errors, they follow a law of probability. Okay, now we shall say this is a standard deviation bell curve. So this is giving us the probability of our measurements. So these are our values. These are our values. The central zero, that means there we have zero error. So it's like this. So, okay, so we are carrying out some measurement. Here we have zero error. So it means that this value should have been the correct value. But our measurements are everywhere. It's like this. Our measurements are everywhere. Okay. But this is following a law of probability. This is following a certain pattern. And the pattern is that most of the values are going to be closer to the actual value, right? Most of the values are going to be closer value. Say, for example, these actual values should have been 100 meter or kg or something. So our measurements, it is most of the time, I'm measuring, you are measuring, our friends are measuring, okay? So our all measurements are going to be very close to the original value, most of the values, okay? The probability that someone will get 300 in place of 100 is going to be very less. Probability that our friends are getting 101, 102, 103, 105, 110, that type of values instead of 100 is very high. So that is this law of probability. Okay. So here we have lower values. Okay, so say for example this was 100, just for example. Okay, this value is say for example 200, and here 150. So most of our friends are getting values which are near to 100. Some are getting 150 and very less are getting 200, and no one is getting beyond that, like this. Okay, so this is our central value, say for example 100. So the probability that people getting positive and negative is equal. Okay, some people will get more than 100, some people will get, or some measurements will be less than 100. So here is the average performer, we're calling it 68%. So here in this dark blue region, 68% of the values or the measurements will lie. Okay, that is called one standard deviation. Okay, here it is written minus 1 sigma, here it is written positive 1 sigma. So the concept is that out of all the measurements, if we are measuring 1000 times, 68% of the values will lie within this category. So that is the idea. So then again, when we are carrying out measurements, we don't actually know what should be the true value. What would be the true value? It is actually indeterminate because there are always some errors involved. We are measuring and we are getting, say, for example, 25 meter or 25 kg or 25 Newton. But by nature, there will always be the probability of some error. So we do not know actually what is the true value. So what we will do, we will take 10 measurements, say for example, and we will find out what is the average of those 10 measurements. If the average is, say for example, 25.5 some unit, then we shall consider that, okay, 25.5 is the true value or most probable value, because that is the average of all the measurements. Okay, so this concept of most probable value is nothing but a mean of all the measurements that we have carried out. So then residual error or the error will be given by the measured value minus the most probable value or mean value. Okay. Then we will do some numericals based on this. Then the all the concepts will be clear. We will discuss some numericals. Then the concepts will be clear. Now here we have few definitions. One definition is weight of an observation. Okay. What is weight of an observation? Say uh, there is one data, we measured it only once. There is another data that we measured 4 times or 5 times. Okay. Now, because we measured the other data only one, and here this data we measured 5 times. So the weight of the second observation is higher. That means the probability that the second observation is correct is higher because we have measured it 5 times, and we should consider the average of 5 readings. So we can say that the second observation that we made, that is weight 5 than the first one, or the probability is 5 times higher that this second observation will be correct. Okay. Then most probable value that we have already discussed, it is the mean of all the measurements we have done, and it is said that this is the value which has the highest chance or probability of being very close to the true value. Okay, that the observed value is the one that we have measured and corrected for some errors. Then most probable error. Okay, just now we saw that okay, we have a distribution like this of the values that we have measured. Most of the values are here very close to the true value or mean value, but this is the value here. This is 50% of our value. Okay, so This limit we are considering it most probable error. Okay, 50%. That is by definition. Okay. Then uh, then we have this definition of standard deviation. So what is standard deviation here? The minus 1s and positive 1s, that is one standard deviation. 2s is the second standard deviation. So it is a value, it is a numerical value of all our measurements. Okay, this is going to give us a standard deviation is a numerical value. Say for example, the mean value is 100, and say for example standard deviation is 15. So the probability that our values will lie between 100 plus 15, that is one standard deviation, 115, and 100 minus 15, that is 85, that is minus one standard deviation, is how much? 34.13 plus 34.13, right? 56. Sorry, 68%. Okay. So 68% is the probability that our values will lie between one standard deviation, positive and negative. Similarly, we will have another numerical value, which is 2 standard deviation. Now, the probability that values will lie between minus 2 standard deviation and plus 2 standard deviation is how much? This 34.13 plus this 13.59 multiplied by 2 for both sides, 95.44% of the cases. Okay. When we go to third standard deviation, which is this 99% of the cases. So this is the concept of standard deviation. We have a formula for finding out standard deviation. Maybe you know that already because you had this in statistics, right? So here the distribution is like this. Here the distribution is like this. So here we have a smaller standard deviation. That means all our measurements are very close to the mean value. And here we have a larger standard deviation. That means our measurements are not so close to the mean value that way. So here we have this formula for standard deviation. Variation, we will see it when we do the numerical. Okay, then we have a formula for standard error of the mean. Then we have a formula for most probable error. The most probable error is corresponding to 50% error. Okay. And then we have a maximum error. The maximum error is 99.9%. Okay. So 50% we call considered most probable error. Somewhere here we have 99.9%. That is our maximum error. Okay, if any value which is beyond this limit, then there is a gross mistake. That is an absolute mistake, and we are going to ignore that value. That value we are not going to consider in our average calculations like this. Okay, so that much will be for today. Please go through this one. We will again discuss the numericals, the formulas when we discuss the numericals. Along with the numericals, we will discuss the formulas and how to solve the